Every night, enormous oil tankers silently cross the Atlantic Ocean, carrying tens of thousands of tons of crude oil through open waters. From a distance, they look like ordinary cargo ships, but beneath that massive steel hull lies one of the most advanced engineering systems ever built. A modern supertanker isn't just a ship, it's a carefully balanced floating machine where every ton of weight matters. At this scale, even a small mistake in how the cargo is distributed can change the behavior of the entire vessel. Surprisingly, the greatest danger doesn't come from towering waves or violent storms. It comes from what's inside the ship itself. Unlike solid cargo, crude oil never stays still. As the ship rolls with the ocean, the liquid begins shifting from side to side, creating powerful forces that constantly affect the vessel's stability. The larger the tanker, the more difficult it becomes to control these invisible movements. That's why modern oil tankers are divided into dozens of separate cargo tanks. Sophisticated loading systems continuously monitor and redistribute the liquid, helping the ship remain balanced even while battling rough seas. But this raises an interesting question. If the ship is already carrying thousands of tons of oil, why do engineers deliberately fill some of its compartments with ordinary seawater? The answer reveals one of the most important engineering secrets behind the world's largest ships.
A fully loaded tanker faces countless dangers during its journey across the ocean. Yet surprisingly, the most dangerous moment often comes when it's completely empty. It sounds backwards, but an unloaded oil tanker can be far more vulnerable than one carrying over 100,000 tons of cargo. Without that enormous weight pressing the hull into the water, the giant steel vessel becomes unstable. Powerful ocean forces begin acting on the ship in ways that most people never imagine. As waves lift the hull, the massive propeller, sometimes weighing dozens of tons, can partially rise above the water's surface. Instead of pushing against water, it starts spinning through air, creating violent vibrations that place tremendous stress on the engine and drivetrain. But the real nightmare isn't the propeller. It's the ship's own steel structure.
As enormous waves pass beneath an empty tanker, the hull bends under incredible forces. Engineers call this phenomenon hogging and sagging, and it's one of the greatest structural challenges in shipbuilding. Imagine the bow and stern riding on the crests of two separate waves, while the middle of the ship hangs unsupported between them. For a brief moment, hundreds of meters of steel are suspended under their own weight. The deck is stretched under immense tension, while other parts of the hull are squeezed together with crushing pressure. These forces become so extreme that without proper engineering, the steel itself could crack, threatening the integrity of the entire vessel. Moments later, the opposite happens. The center of the ship is lifted while the bow and stern lose support, reversing the stresses throughout the structure. With every passing wave, the ship constantly flexes back and forth. Managing these enormous forces is one of the greatest challenges of operating a supertanker. To overcome these dangerous stresses, engineers rely on something unexpected. They use the weight of the ocean itself. Hidden deep inside the ship's double bottom are specially designed ballast tanks. These compartments can hold thousands of tons of seawater, adding precisely the right amount of weight where it's needed most. By carefully pumping seawater into different ballast tanks, operators lower the ship deeper into the water and restore its proper balance. This extra weight stabilizes the hull, keeps the propeller fully submerged, improves steering performance, and dramatically reduces structural stress during heavy seas. But managing ballast isn't as simple as filling a few tanks. Every valve, every pump, and every transfer must be carefully controlled. Even a small mistake can create a life-threatening imbalance. That danger became painfully clear in July 2006. Near Alaska's Aleutian Islands, the vehicle carrier Cougar Ace was performing what should have been a routine ballast transfer while transporting nearly 5,000 brand-new automobiles. Then, something went wrong. A malfunction in the ballast control system caused seawater to flow unevenly between the ship's tanks. Within minutes, the massive vessel developed an astonishing 60-degree list before collapsing onto its side in the middle of the ocean. Electricity failed almost instantly.
Crew members found themselves trapped inside a dark steel maze as floors became walls and walls became ceilings. Salvage experts spent weeks calculating the precise movement of every ton of water before they could safely return the ship to an upright position. The accident proved a critical lesson. Inside a ship, water can be just as dangerous as the sea outside.
Many people believe ballast is nothing more than extra weight added to stop a ship from blowing around in the wind. But that's a common misconception. In reality, ballast is a sophisticated engineering tool used to control how the ship's entire structure responds to enormous forces. The weight of seawater helps distribute stress throughout the steel hull, preventing dangerous bending during rough weather and protecting the vessel from structural failure. Without it, even the strongest tanker would be exposed to forces capable of damaging its massive frame. Yet solving one problem creates another. As soon as the cargo tanks are emptied, a completely different danger begins to appear, one that can't even be seen.
When crude oil is unloaded, the tanks aren't actually empty. A thin, nearly invisible film of oil always remains on the steel walls. As this residue slowly evaporates, it releases highly flammable hydrocarbon vapors that begin mixing with oxygen inside the enormous cargo tanks. Within a short time, the perfect conditions for an explosion can develop. In fact, an empty oil tanker can become far more dangerous than a full one. Sometimes all it takes is a single spark of static electricity to trigger a devastating explosion, powerful enough to destroy the entire ship. The danger builds silently. No flames, no warning. Just invisible gas waiting for the smallest ignition source. To eliminate this hidden threat, engineers developed one of the smartest safety systems ever installed on a ship. Instead of allowing normal air to fill empty cargo tanks, modern tankers replace it with inert gas. Surprisingly, that gas comes from the ship's own engines. Exhaust gases are captured and sent through special treatment systems where they're cooled with seawater, cleaned of soot and contaminants, and processed until the oxygen concentration drops below 5%. This oxygen-poor gas is then pumped into the empty cargo tanks. Without enough oxygen, combustion simply cannot occur. Even if a spark appears, there's nothing left to ignite. The ship is effectively protected by replacing breathable air with an atmosphere that fire cannot survive in. This life-saving technology wasn't adopted by chance. It was written in blood. In December 1969, 3 separate supertankers, Marpessa, Mactra, and King Haakon VII, suffered catastrophic explosions while sailing without cargo. Each vessel was carrying out routine cleaning operations inside empty cargo tanks using high-pressure water jets. As the powerful streams struck the steel walls, tiny droplets filled the air, creating enormous amounts of static electricity. Eventually, a single spark ignited the accumulated hydrocarbon vapors. The explosions tore through the ships with devastating force. One of them, the 200,000-ton supertanker Marpessa, suffered such severe damage that it eventually sank off the coast of West Africa. Those tragedies permanently changed international tanker safety standards and led to mandatory inert gas systems on modern oil tankers. Even today, many people assume that once the oil has been unloaded, the danger is over. In reality, that's when some of the greatest risks begin. An empty cargo tank can contain the perfect mixture of oxygen and flammable vapors, making it far more hazardous than a tank completely filled with crude oil. Protecting those tanks is only one part of the challenge. The next problem is even harder. Imagine trying to stop a steel giant weighing hundreds of thousands of tons in the middle of the ocean. Unlike a car, a supertanker has no brakes. Once it's moving, its enormous momentum becomes one of the most powerful forces on Earth. And bringing that giant to a complete stop is a challenge unlike anything most people have ever imagined. When an emergency appears ahead, bringing a supertanker to a halt is far more difficult than most people realize. A fully loaded tanker doesn't stop in a matter of seconds or even minutes. Even after the captain orders full reverse, the ship may continue moving for nearly 9 kilometers, carried forward by its enormous momentum. For the crew on the bridge, this creates a terrifying situation. They may spot an obstacle miles ahead, fully understand the danger, and still know there's little they can do to stop the ship in time. The vessel's immense kinetic energy transforms it into a moving steel battering ram. Once that momentum builds, no conventional braking system can overcome it. When the captain decides an emergency stop is unavoidable, a carefully rehearsed procedure begins. The main engine is shifted into full reverse. Deep beneath the stern, the enormous propeller changes direction and starts forcing water forward instead of backward. From above, it looks dramatic. The sea erupts into white foam as the propeller churns the water with incredible force. But appearances can be deceiving. Despite everything the engines are doing, the tanker barely slows during the first several minutes. Physics simply refuses to cooperate. The ship's colossal mass keeps pushing it forward through the ocean, long after the engines are fighting against its motion. Momentum remains in control.
No ship demonstrated this challenge more dramatically than the legendary Seawise Giant, the largest vessel ever built. Stretching an astonishing 458 meters in length and displacing more than 560,000 tons, it dwarfed nearly every other ship on Earth. Stopping such a giant required extraordinary planning. Captains often had to begin reducing speed many kilometers before reaching their destination. Even a slight miscalculation could leave the vessel unable to stop where intended. Its enormous size created other limitations as well. The ship was simply too large to pass through the Suez Canal and struggled to navigate many narrow waterways around the world. Operating a vessel of this scale demanded precision unlike anything found in ordinary shipping.
In May 1988, the Seawise Giant faced one of the greatest challenges in its history. While operating in the Persian Gulf, the tanker suffered severe external damage that triggered a massive onboard fire. Flames spread rapidly, and the crippled vessel eventually settled in shallow water. For most ships, damage on this scale would have meant total destruction. But the supertanker's internal steel structure proved remarkably resilient. Its network of reinforced bulkheads absorbed tremendous forces, preventing the entire hull from collapsing. Years later, the vessel was successfully salvaged, repaired, and returned to service. Its survival became a powerful demonstration of just how strong modern tanker construction had become. In May 1988, the Seawise Giant faced one of the greatest challenges in its history. While operating in the Persian Gulf, the tanker suffered severe external damage that triggered a massive onboard fire. Flames spread rapidly, and the crippled vessel eventually settled in shallow water. For most ships, damage on this scale would have meant total destruction. But the supertanker's internal steel structure proved remarkably resilient. Its network of reinforced bulkheads absorbed tremendous forces, preventing the entire hull from collapsing. Years later, the vessel was successfully salvaged, repaired, and returned to service. Its survival became a powerful demonstration of just how strong modern tanker construction had become.
Over the years, countless myths have appeared online about how giant ships perform emergency stops. Some people believe modern tankers carry huge deployable brakes hidden beneath the hull. Others claim they can simply drop their massive anchors while moving at full speed to stop instantly. Neither idea is true. Releasing an anchor at cruising speed would create catastrophic forces. The anchor chain would tighten almost instantly, generating loads so enormous that it could rip the windlass from the deck and severely damage the bow itself. For ships of this size, emergency stopping depends entirely on careful planning, engine control, and understanding momentum. There are no shortcuts, only physics. Even after a tanker successfully slows down, another challenge remains. The ocean never stops pushing.
As these massive vessels travel through narrow channels and busy shipping lanes, external forces continue acting on every part of the hull. Protecting both the cargo and the ship itself requires more than skilled navigation. It requires an entirely different approach to ship construction. Engineers eventually realized that traditional designs were no longer enough. To make modern tankers safer, they completely reimagined the structure of the hull itself. The solution would forever change the shipping industry. Over the years, countless myths have appeared online about how giant ships perform emergency stops. Some people believe modern tankers carry huge deployable brakes hidden beneath the hull. Others claim they can simply drop their massive anchors while moving at full speed to stop instantly. Neither idea is true. Releasing an anchor at cruising speed would create catastrophic forces. The anchor chain would tighten almost instantly, generating loads so enormous that it could rip the windlass from the deck and severely damage the bow itself. For ships of this size, emergency stopping depends entirely on careful planning, engine control, and understanding momentum. There are no shortcuts, only physics. Even after a tanker successfully slows down, another challenge remains. The ocean never stops pushing. As these massive vessels travel through narrow channels and busy shipping lanes, external forces continue acting on every part of the hull. Protecting both the cargo and the ship itself requires more than skilled navigation. It requires an entirely different approach to ship construction. Engineers eventually realized that traditional designs were no longer enough. To make modern tankers safer, they completely reimagined the structure of the hull itself. The solution would forever change the shipping industry. For decades, nearly every large tanker was built with a single steel hull. Only one layer of metal separated millions of gallons of oil from the surrounding ocean. The design was simple, efficient, and relatively inexpensive. It also maximized cargo capacity, but it came with one enormous weakness. If the hull was punctured below the waterline, there was nothing left to stop seawater from flooding in or crude oil from pouring out. A single impact could instantly turn an ordinary voyage into an environmental disaster. Engineers knew the risk, but for many years, there seemed to be no practical alternative. Everything changed in March 1989. Off the coast of Alaska, the oil tanker Exxon Valdez accidentally struck Bligh Reef after leaving the designated shipping lane. The collision ripped open the ship's single steel hull within seconds. Tens of thousands of tons of crude oil spilled into the pristine waters of Prince William Sound, creating one of the worst environmental disasters in maritime history. The response came quickly. In 1990, strict new regulations began requiring oil tankers to adopt double hull construction. Instead of relying on a single steel shell, engineers created two separate hulls with an empty space approximately 2 meters wide between them. During a collision, the outer hull absorbs much of the impact, while the inner hull continues protecting the cargo tanks. Even if the outer layer is damaged, the oil often remains safely contained inside. Under normal operating conditions, this protected space also serves another important purpose. It houses the ship's ballast water, allowing the vessel to maintain stability while adding another layer of protection around the cargo. Many people assume that double-hull tankers are virtually indestructible. Unfortunately, that's another myth. Creating this hidden space between two steel walls introduced a completely new engineering challenge: corrosion. These narrow compartments remain dark, humid, and constantly exposed to seawater, creating ideal conditions for rust to spread. To prevent structural damage, maintenance crews must regularly enter these confined spaces through small access hatches, carefully inspecting every meter of steel with flashlights and specialized equipment. The double hull dramatically improves safety against collisions and groundings, but protecting the ship now requires constant vigilance against an enemy that attacks from within. And while corrosion threatens the ship in open water, an even stranger danger appears in places where the sea seems perfectly calm: narrow canals. There, an invisible force can suddenly overpower even the captain's steering commands.
The next time you see an oil tanker slowly crossing the ocean, remember that you're looking at far more than a giant steel ship. You're witnessing decades of innovation, engineering brilliance, and hard-earned lessons that have transformed these colossal vessels into some of the safest and most advanced machines ever built. Despite their incredible size, every successful voyage depends on an invisible balance of physics, precision, and human expertise. If you enjoyed discovering the incredible science behind these engineering giants, don't forget to like the video, subscribe to the channel, and turn on notifications so you never miss our next deep dive into the world's most fascinating machines and technologies. Thanks for watching, and we'll see you in the next video.